We have yet another alternative, which is to sense at the source and feedback to the gate. Okay. Because the drain is not in this picture, we are sensing at the source and feeding back to the gate. I will connect the drain to the supply voltage. Okay, it's some voltage, it's connected somewhere. As far as the biasing circuit is concerned, it's not relevant where the drain is connected to. Of course, in an amplifier, we would like it to be connected such that it remains in saturation region. Now, to sense at the source, I connect the current source I0 to the source terminal, and we have the actual drain current ID in the MOS transistor. Now, we are feeding back to the gate. Earlier, in our very first case, we were feeding back to the gate and we connected the source terminal to ground. But of course, now we are sensing the current difference at the source terminal. So, we cannot connect the source terminal to ground. Okay. So, the source terminal is connected to the current source and we have to feed back to the gate. Okay. Now, the source terminal is not exactly fixed, but still we can go through our chain of reasoning. If ID is too large, that is, it's larger than I0, what must happen? VGS must reduce. Okay. So, VGS must reduce. We don't know what the source voltage is, but because VGS equals VG minus Vs, if we are trying to control it with VG alone, then this says that VG also must reduce. Okay. And this is the feedback action that we want. That is, if ID is larger than I0, then we must reduce VG so that ID tends to reduce. Okay. Now, let us see what actually happens at the source terminal. ID minus I0 flows into the capacitor, and if ID is higher than I0, what happens is that the source voltage Vs actually increases. Okay. So, what is happening to the source voltage is a measure of whether ID is greater than I0 or less than I0. If ID is greater than I0, Vs increases and we want to reduce Vg. So, that means that like in the previous case, there must be a negative incremental gain between Vs and Vg. That is, if Vs increases, Vg must reduce and vice versa. So, we can connect some block that takes Vs as input and puts out Vg, and it must have a negative incremental gain, meaning its output reduces as the input increases. Okay. Right. So, that is the meaning of negative incremental gain. Okay. Now, one thing you observe here is that from our earlier discussion, you know that this is Vg and I connect I0 to the source terminal, and there is the actual drain current ID. And if ID is greater than I0, ID minus I0 flows in this direction into the capacitor and raises the source voltage. Now, the current ID is also dependent on the source voltage. Okay. So, as source voltage increases, ID tends to reduce. Okay. So, there is already feedback just by this connection, and in fact, if this voltage, the gate voltage, was fixed, this is our older circuit. This is sensing at the source and feeding back to the source. So, when you connect a current source to the source terminal, there is already feedback to the source. Okay, this you cannot remove because source terminal belongs to the controlling part of the MOSFET as well as the controlled part of the MOSFET. Okay. Now, when you connect this additional circuitry here, there is also feedback to the gate. Okay. So, really in this circuit, although I called it sensing at the source and feeding back to the gate, we are sensing at the source, that is correct, but the feedback is both to the source and the gate, and both are in the appropriate directions. Okay, because if ID is more than I naught, then Vs increases, and through this negative incremental gain, Vg reduces. So Vgs definitely reduces. Okay, but this is still a different case from the earlier case we discussed where the gate voltage was fixed, because now we are feeding back to both the gate and the source, and typically the feedback to the gate is much stronger. So it is useful to treat this as a special case. So we have now discussed all four cases, sensing at either drain or source and feeding back to either gate or source. Okay. Again, this circuit is slightly more complicated than the first two types of feedback biasing that we discussed. So just for a common source amplifier, you would probably not use this, but there are many other circuits in which such an arrangement appears. Okay. And I'll quickly show you one possibility, again using an ideal op amp. I had to sense Vs and feed it back to the gate, and I do it through an op amp, and the other terminal of the op amp I call Vs0. Now we know that we want a negative incremental gain between this Vs and Vg, so it has to be of this sort. The signs of the op amp must be like this. Okay, and this is the differential voltage of the op amp. Now if you look at the rest of the circuit from this Vg to Vs, okay, you will find that this is the correct sign of these are the correct signs for the op amp to ensure negative feedback around the op amp itself, because the op amp gives you this virtual short property only when it's in negative feedback. Okay, as far as we are concerned, we can say that the op amp must be in negative feedback, that's all. Okay, there are some useful circuits where the op amp may be in positive feedback, but as far as we are concerned, in all our op amp circuits, the op amp will be in negative feedback. Okay, so this concludes the four types of bias circuits, that is sensing at the drain, feeding back to the gate, sensing at the source, feeding back to the source, sensing at the drain, feeding back to the source, and sensing at the source and feeding back to the gate. Okay, so as long as you understand the basic principle, it doesn't matter in what exact manner these things happen. Okay, meaning we may connect the drain directly to the gate, or we may have some other circuitry in between, and so on. You should be able to analyze all of them, because now you know exactly why these circuits establish the correct operating point current in the transistor. Okay.